Uh, Thanks everybody for joining our next Center for Satellite Earth Science Research webinar slash seminar. This is our new center known as GMU-CSER at George Mason University. And we're really excited that today we have a presentation by Professor Lucas Henneman of George Mason University. And on a really important topic in understanding how air pollution and exposure from different sources impacts human health. And so this is a very important topic, very impactful. And introducing Dr. Henneman, he is an assistant professor of environmental engineering at George Mason University. That's in Fairfax, Virginia. He studies relationships between air pollution emission sources, air quality, human exposure, and human health. His recent work involves developing and applying models that enable exposure studies of large numbers of individual air pollution sources. Prior to his current position, Dr. Henneman completed his postdoc at Harvard School of Public Health and earned his PhD at Georgia Tech. So with that, welcome, Lucas, and I'll turn the floor over to you for your presentation.
Great. Thanks, Patrick. Thanks for the invitation. Nice to see you all here. So it's a reasonably small group. So if I say anything that's confusing or you have questions about, just, I don't know, raise your hand or type something in the chat. I'll try to keep an eye on it, and we can talk about it as I go through.
Yeah, Lucas, sorry to interrupt, but yeah, if we can, I think it's great to keep open discussion if that's fine. Yeah, and if people have questions, we can maybe stop along the way if that's okay with you, as you just mentioned.
Of course, yeah, I don't think this has to be so formal from my perspective.
Great, that's a great idea. Thanks.
Yeah. So let's see, for those in, okay, now I can have this laser. All right, fun. For those in the room, I think I'll sit down so that I can drive here on my laptop. So basically, I'm gonna give kind of 3 headline messages in this talk. Number 1, just sort of the introduction, that calculating sources, and by that I mean source categories contribution to PM 2.5. So thinking like power plants or automobiles, wildfires, it's important. That's number 1. I'm going to talk about some work I did that's getting old now, but still relevant, and we've done some updates on it about PM 2.5 from coal power plants and how it's particularly bad for mortality. But we've made a lot of progress since about 2007. And then some more kind of hot off the press research on air pollution, PM 2.5 sources since 2010, and how there's been this major shift in the most important PM 2.5 sources across the entire country. So, part 1, why am I thinking about this? Well, we'll go back about 2,000 years or so, and just establish that we've known that air pollution is bad for us for a really long time. So here's Seneca the Younger in 61 CE, writing about how he has been consigned to one special ailment, and he was describing asthma. Who indeed could breathe his last for so long? There are many examples of writers and philosophers complaining about how they're getting sick when there's air pollution, and how they can do a personal intervention and leave the polluted locations and feel better. So from that perspective, you know, this explosion in air pollution and health research in the last few decades has served to quantify these effects, but not explain that they were there in the first place. From a health and PM 2.5 perspective, the major initiating study was this Harvard 6 Cities study 30 years ago now, where they had mortality data in 6 different Midwestern cities, industrial cities, and they also measured PM 2.5 concentration. So here, each of the letters is a different city. Uh, PM 2.5 concentration is on the x-axis. The y-axis is the rate ratio. So you could think about that. I think the way they defined it is the relative likelihood of death relative to this cleanest city. And they didn't expect that they would see this nice straight line that where in areas with higher concentrations you had a higher mortality rate, but they did. And this there's a long history associated with this study. There's a new book out called Particles for Truth by Doug Dockery and Arden Pope, describing about how they got attacked in the press for this study, but it's really stood the test of time. There have been many other studies since then looking at chronic exposures and linking PM 2.5 to death, but also short-term endpoints like COPD, for example, and asthma. Again, really quantifying those things that the Romans knew 2,000 years ago. But that type of evidence has been important, so we've been able to develop estimates then, and depending on how you count these things, you get slightly different answers, but by the one estimate, there are about 4 million deaths from PM 2.5 per year worldwide. But I'll come back to the PM 2.5 as kind of an interesting measurement. Um, there might be some relevance that different sizes of particles end up in different parts of our body. So maybe PM10 only ends up to like our throat, and PM 2.5 ends up in our lungs, and PM1 can penetrate even further. But really, it's a measurement based on convenience. It's relatively straightforward to filter out particles that are different sizes and quantify their mass in the atmosphere. But there's been this ongoing question for a long time of whether the chemistry of the particles is actually a more relevant measure to health. And that also ties to sources, as we'll discuss in a moment. Sources like power plants or cars also comes from things like wildfires or dust storms. Each of these has their own chemical signatures associated with the particles from those sources. And so that leads to some research questions, some of which I'll answer here, some of which are more provocative. So first, which sources cause the worst air pollution? Who's exposed to which sources? How has exposure to these sources changed over time? What led to those changes over time? What are the health impacts of specific sources? And then, really this all sort of comes together in which sources do we be most concerned about if we're worried about protecting health in the future. So that's my motivation then for the next 2 parts. Part 2 here is PM 2.5 from coal power plants is particularly bad from health, but there's been this major improvement since around 2007. And so for background here, in 2005, the electricity generation, so power plants and especially coal power plants, contributed 12% of primary PM 2.5 emissions, 16% of NOx emissions, and 70% of SO2 emissions. So these are major source category in the United States. And other people had looked at this time at how this source category had contributed to mortality in the United States. So this study in Nature. This was my friend, actually, Irene Deducci, who used geoschem adjoint to link premature deaths to specific sectors. So in 2005, they found that 24,000 deaths total were linked to electricity generation. 2018, that number dropped pretty steeply by about 2/3 to 8,500. And this isn't the only type of estimate like this, but they also have some similar assumptions baked in. The first is that the health risks that they used were inferred from previous epidemiology studies. So they weren't looking at the health risks specifically of US electricity generation pollution. As I said, PM 2.5 from different sources could be differently toxic. And they assume that that was not the case, that all the PM 2.5 is the same. It has the same health effects as it always has. Okay, so with that background, we wanted to look into coal power plants as a source that might be contributing differently to the PM 2.5 health impacts than other sources. And for those who may not know, most of the coal power plants in the US are in the east, or were historically in the east, still are. This is from 2005, and probably the spatial distribution today looks similar, although there are fewer points because many coal power plants have closed. The biggest ones tend to be along the Ohio River Valley here, with a couple big ones that are still operating in Texas and in the southeast. And if we look at emissions, which is down here on the bottom, since 2000 to 2020, they've come down about 90% since over this 20 years, and essentially kind of held steady until 2007, and then there was this major decrease. So with this study, we set out to answer three questions. One is, what led to those reduced SO2 emissions and subsequently exposure from coal power plants? The second, how have air pollution exposure inequalities changed with SO2 emissions reductions? And the third, how has the health burden changed with the SO2 emissions reductions? And I'm going to talk today about the first question and the third question. We'll talk about exposure reductions and health improvements. So this is a lot of facilities. Trying to remember, there are a couple hundred facilities across the whole US. And we really wanted to dig into this on a facility by facility basis because the emissions changes are unique to each facility. This major trend, while there's some features you can draw out, is going to have differences depending on the specific facility, and that's going to map to different populations exposed. So what we came up with was to use high split. And we developed this approach where basically we run high split 4 times per day for each facility location for these 22 years. And this is showing from a big power plant just north of Atlanta, the high split trajectories from February and July. We emitted 100 air parcels 4 times per day, and then aggregated their locations and weighted those aggregated locations by monthly SO2 emissions. And you can see it picks up some interesting features, like in July, there's sort of a stagnation event here where a lot of people are exposed. You get different kind of doubling back of these parcels. So like here, and feel reasonably confident that we're picking up the actual exposure patterns from these power plants. We did a lot of comparisons with more complex models and ground-based observations. And at least, this is showing or day by day, but on a annual concentration level, we feel pretty confident that we're getting the contributions from power plants, the spatial representation. Now, this is just giving us parcel locations weighted by SO2 emissions. What we really wanted was the contributions to PM 2.5. So we had at our disposal CMAC, DDM output. So these are sensitivities to SO2 emissions. And these came on a spatial grid. They were in 2 of the years here. We used a regression against those values to get our concentrations in PM 2.5 units. And then, for example, if we aggregate for a different facility over the entire year, we end up with a concentration field that looks like this for a single facility. And excuse me for not putting units on here, but I promise they're reasonable. The next slide has units. So here's sort of aggregated exposure from all facilities for these 4 snapshot years in our time series. The bottom of the scale is 0 and the top of the scale is 2. You can see in 1999 and 2006, there's really high contributions from coal to PM in the eastern US, a few hotspots in the west. 2006 looks a lot like 1999. Then by 2013, there are major reductions, and 2020 looks basically free of PM 2.5 from coal, although there's still some light shading still around Texas and the Ohio River Valley. So we had this big, for each power plant, we had this big time series of who was exposed and how that exposure changed over time. And we use it, the next question was sort of what drove those changes over time. And so we, for each power plant, estimated a contribution to population weighted exposure and plotted it on a time series that looks like this. So this is 1999 is on the far left of the axis, 2020 is on the far right. And you can think about this as a measure of population weighted exposure. And so I'll tell you what the different colors are. The gray colors are the exposure that actually happened. And the exposure that actually happened came from 2 types of coal facilities. It came from facilities without a scrubber installed. So in 1999, that's most of the exposure is coming from facilities without scrubbers. And it's also coming a little bit from facilities with emission controls installed. Now, both of those sort of drop off around that 2007, so actual exposure decreases. Then the reason for that decrease is coming from a few different reasons. One of them is exposure that's avoided because units retire. So they either avoid exposure after they've installed their scrubber, or they avoid exposure by retiring before a scrubber is installed on those units. By far the biggest reduction is the actual installation of the scrubbers on some of these units. So even more so than retirements. And finally, this kind of narrow band in the middle is a reduced operation. And there are 2 colors there. It's either reduced operation on units that have a scrubber or reduced operation in units that don't have a scrubber. And I'll pull out sort of 3 time series or 3 periods of interest here that might be related. So this is the same figure as I just showed. In 2006 to 2011, that's when you see this big growth in the light blue. That's when a lot of these facilities were installing scrubbers. That was regulation driven. 2008 to 2012. Anybody know what happened in 2008 that would lead to reduced operations? Yeah, the recession. So we see that show up in the data. Basically, it's the peak electricity demand in the US was 2007. And it's just now starting to reach back to what it was in 2007 because of the data centers. And then after 2012 was when a lot of retirements happened. We see those showing up. And many of those retirements are driven by natural gas getting more competitive on price with coal. So it's, nice to see those quote interventions or real world impacts on the actual exposure side that we can tie this to. We also linked the exposure to health, and I'm skipping a lot of the nitty gritty, but this was based on epidemiology using the Medicare population. And so we linked our exposures, our annual exposures here with mortality rates in the Medicare population and estimated a concentration response function from that, but then used our exposure data to, for each facility, measure its contribution to mortality. And so there's a few things going on this plot. Just to orient you, we have the years on the x-axis, and then we have the annual excess deaths attributable to coal. And so we look at this study where we estimated the concentration response function that was specific to our exposure. We get about 500,000, just under 500,000 total deaths across the entire period. And again, those start pretty high up until about 2007, and then the number of deaths attributable to coal really drops off as emissions drop off. Now, if we'd used other estimates of the concentration response function, we would have ended up with a lot lower total deaths, about half as many total deaths. And so we were able to show that, by developing this health response function that was specific to our source, specific to coal, we found much higher number of deaths attributable to coal, but also a bigger improvement over time than these previous models would have shown. So that's my headline one. This was fun. I mean, we got to publish in Science, and there was a lot of press associated with that. John Kerry was talking about us at the COP and mentioning George Mason, so that was fun to get our name in the news. Yeah, I'm happy with how the study went out. There was also some negative attention towards me, which I'm happy to talk about in questions too, if people are interested, although that might not be that interesting. One of the things that came out of this and we kept getting asked about was, okay, you found that coal was harmful, but coal is closing, those numbers of deaths towards the end of the study period are much lower than the beginning. Do we really have to worry about it anymore? So we're just finishing up a study now where we're looking at the counties that EPA projects won't be in attainment of the PM 2.5 NAAQS in 2032. And actually, so this next map, these are the 32 counties that EPA, based on their modeling, thinks won't be in attainment in 2032. And we ran CMAQ with DDM, it's a direct decoupled method to look at the contribution to PM 2.5 from coal SO2 emissions. And we found that in the These 7 counties in red here, by closing or eliminating SO2 emissions from coal power plants, those counties could actually meet the attainment without making any additional cuts based on EPA modeling. And because we had this reduced complexity model that we could look facility by facility, we could also investigate the additional benefits. So 2 would be, so here we have each county that could achieve attainment on the x-axis. On the top plot here, we have the premature deaths avoided if enough coal plants close to enable them to meet the standard. And on the bottom is the SO2 emissions avoided. And there are 2 colors. One is the power plants that don't have current retirement plans, and the yellow is the power plants that do have current retirement plans. And so for Lebanon, Pennsylvania, for example, over 400 deaths in the Medicare population per year would be avoided if they closed enough coal power plants to achieve the standard. But it's not, those aren't the facilities that have the most emissions reductions. That's coming from Armstrong, PA. So interesting sort of policy angle using our model here, looking to the future. Okay, how's everyone doing? Does that all make sense? If you have questions, let me know. Otherwise, I'll go to part 3 and we can discuss at the end. This is more recent work. Oh yeah, and the last, this is done by my student who just graduated, Munchi Razel, and Ting, who's a postdoc who's been working with me, and Sumaya have been working on this next study. And so we've been trying to do this on a more systematic basis for more sources than just coal power plants, is the impetus here. And so there's been, as you'll see, there's been this real change in the landscape of PM2.5 sources. And so our goal with this study is across the entire US daily PM2.5 source impacts fields. And why might we be interested in that? Additional motivation from the first part of this talk. Well, in a number of recent studies, so for example, this one by Zhao Wu, they keep finding PM2.5 health impacts at lower and lower concentrations of PM. And so we don't really know why that is after assuming, but also it suggests that we're going to have to come up with more and more targeted emissions cuts to reduce the health impacts. And as I said before, sources contribute uniquely to exposure, health, and exposure inequalities. There's sort of inconsistent results in the literature about which sources are contributing the most to health impacts. We set the NACs that I was talking about, the air quality standards for the ambient environment, but interventions necessarily have to target sources. So wouldn't it make sense if we targeted the most impactful sources? And finally, so if we could do this systematically on a nationwide basis, we can link sources to health and then also to exposure equality in a more systematic way. Okay, so how do we do this? And then I'll show some results. We need a ground truth. So the air quality models can give us an estimate about which sources impact which locations, but it's hard to evaluate those models. And so to get that ground truth, we used source apportionment at US monitors. There's about 300 monitors across the US that are measuring species on a day-to-day basis. This is the CSN network and the improved network. And so we ran source apportionment at each one of those 300 monitors to get daily source impacts at each monitor. It was a lot of work. Then also used chemical transport modeling. So we used CMAC and equates. This group uses, we tapped into some of the emissions processing that you all had done here. But to get gridded PM 2.5 source impacts, they're using ISAM. Then combine the two data sets. So basically develop machine learning models to predict the source impacts from the at the monitor locations, and then applied those machine learning models to predict the source impacts everywhere. And then, as I'll show, we're doing some environmental justice work at the end to look at who is exposed and how that exposure has changed over time. Okay, so through the results. So as I mentioned, there are two networks. CSN is mostly urban, Improve is mostly rural. Looking at concentrations for Improve or for CSN sites that are urban tend to be higher. This is total PM 2.5. And at each one of these monitors, we ran positive matrix factorization, PMF, which is a matrix factorization approach that restrains everything to being positive. We also use the dispersion normalization to address atmospheric dilution. And the way we did this, so if you download PMF from EPA's website, or at least it historically was there, you have to click through a lot of times. Ting, my postdoc, figured out how we could run many PMF runs simultaneously on our cluster here at Mason. So we ran with between 3 and 11 factors for each site, and then did a combination of automatic source assignments and some manual source assignments based on nearby sources, previous studies that have been run at these locations, and other factors. And this is what we came up with. So this here, each point represents a monitor. These are the 8 sources or so that we found consistently across the United States. Not every single source was identified at each of the locations. So the list being biomass, industry, non-tailpipe, so tires and brakes, salts, which could be both sea salt or like road salt, secondary nitrate, secondary sulfate, soil and dust, and then traffic exhaust. And then the plots here, there's concentration change between 2011 and 2020, and then the change in the fraction of total PM per year. And so some takeaways. The first is that the 2 source categories with the most decrease nationwide, the biggest being secondary sulfate, that's mostly coming from those same coal power plant SO2 emissions reductions that I showed on the previous slide. And secondary nitrate decreases coming from both power plant and automobile emissions reductions, NOx emissions reductions. Others that are increasing slightly, even fractionally, so biomass being the big one. I think a lot of that has to do with fires. I'm sure a lot of it has to do with fires, and we really see that show up as a major increase. 2 that were a little bit surprising is traffic exhaust ticking up, especially when you look at fraction per year. And some of that is because it's just becoming relatively more important than secondary sulfate. Also soil and dust. And then there isn't much trend in industrial, non-tailpipe, or salt. So that was the PMF at the monitor locations. We also ran CMAC using ISAM, which is a tagging method on the EPA equates 12 by 12 kilometer grid. This is 1 day's exposure from power plants, or PM 2.5 from power plants, for example. We ran this for 9 source categories: power plants, fires, industry, dust and agriculture, gas vehicles, diesel vehicles, other transportation, biogenic, and sea spray. And Sumaya came up with some very nice, colorful plots. Sorry, the text is kind of small. We don't have to go through all of these, but they're kind of interesting. So the 3 sources on the top are all transportation related. The top left is gasoline, the middle is diesel, and the top right is other transportation. They're different colors because the units are slightly different. So the other transportation maximum is much lower than diesel and gasoline. Power plants is here, so we see sort of that similar pattern I showed with the higher concentration in this band. Industry has some urban or local hotspots. Oil and gas is one of our industries. You see the oil and gas basins like the Eagle Ford Shale, for example, show up. Dust and agriculture is interesting. So a lot of the agricultural corridors, like in the Midwest and the San Joaquin Valley in California. Fires has a lot of variability year to year. In this year, 2019, we see a lot of impacts up here in the northern Midwest. Biogenic, lots of biogenic emissions in the southeast, and then sea spray has this nice kind of pattern around the coastlines. Happy to show these later if people want to investigate and try to pick them apart. Also looking at trends over time. Again, sorry for the small text here. Red means cleaner, and blue means dirtier. So for example, power plants is easy to spot. A lot of reduction in the eastern US, not much change in the west because there wasn't much to begin with. Fires are showing up blue. There's a lot more fire activity than there used to be. And emissions cuts from the transportation sources. Okay, so I want to be cognizant of time and we can come back for questions. So we combine those 2 data sets. So we built this model, designated F for a generic function to model PMF source impacts that we observed at the monitors with PMF as a function of multiple predictors. So things like meteorology, land type, day of week, month, year. The CMAC ISAM source impacts that I just showed you. The gas concentrations from CMAC, and then other sources like HMS smoke for wildfires, the toxic release inventory, road proximity. And our models actually do pretty well. So this is showing for a random forest model, trained on all 300 of those sites for 10 years. In a holdout analysis, we have mean bias, normalized mean bias, correlation, and root mean square error. Let's just pick correlation. So each dot represents one of our 50 holdouts. So the correlations for all the models, this is R, not R squared, are above 0.8, which we feel pretty good about. And then normalized mean bias generally within -5 to 5%. And this is for the 5 sources we built models for: biomass, soil dust, secondary nitrate, secondary sulfate, traffic exhaust, and then we built a total PM 2.5 model too. Let's see. And just to kind of finish the thread here, so we built 50 models for each source based on 80% of the data. and then use the median prediction for all of those models on each day as our final prediction. And this is what we ended up with. This is average source impacts in 2019. So biomass burning tends to have high in the southeast. I think that's a lot of the prescribed burning there. And then in California in the west. And secondary nitrate tends to be mostly in the north, where the colder temperatures. Secondary sulfate, mostly in the eastern US. Soil dust is highest in the southwest, and then traffic is highest in the city. So a lot of the sort of initial view of these, I think, meets the gut check reaction. And then what's nice about these statistical models is that we get an estimate of the uncertainty across the models. And some interesting patterns jump out, like the relative uncertainty is highest for nitrate in the west. Partially, I think that's because the concentrations are so low. And then you get interesting patterns with traffic too, I think also with highest relative uncertainty where the concentrations are low. The next slide is just to show off a little bit. So we made these predictions on a daily basis. And so here the rows are each of the sources: biomass burning, secondary nitrate, secondary sulfate, soil dust, traffic exhaust, and then we have a day in January, April, July, and October, and you see very different spatial patterns. So for example, let's pick on secondary sulfate because it's easy to explain. As expected, it's much higher in the summertime. On an October day, there's pretty high concentrations in Texas, but lower elsewhere. For soil dust, depending on the day, you get very different spatial patterns. But traffic is more consistent day to day than the others. Okay, the last thing I'll talk about here, we use these to look at the changes in population-weighted concentrations for different racial and ethnic groups. There's a lot going on this plot, kind of condensed in one. So it's a two-color scale. The bluer colors mean that between 2011 and 2019, there was an increase in overall concentration for that group. And the redder colors mean that the relative concentration for that group compared to the total population got worse. So for example, for total PM 2.5, for Hispanic people, the concentration that they were exposed to decreased overall, but the relative concentration compared to the total population increased. So we didn't really adjust the inequality or address the inequality there as we were decreasing the concentration. And you see different results for different sources. A big one that jumps out is biomass burning, where you have this increase in exposure for everyone. But sort of the main takeaway here is that for most of these sources, even the ones that changed over the time, there hasn't been a change in the exposure inequality between groups. Okay, I'm running out of time, so I want to quickly just show that this is the work of a lot of different people, and I'm lucky to work with lots of really smart and talented people. There are a few other fun things that are going on. I definitely want to highlight the Reach Center, which many of you are a part of. So we're doing a study now of proposed road pricing strategies in Washington, D.C. So we've teamed up with a transportation modeler that's looking at the impact on traffic from congestion pricing, so similar to what they put in New York recently. And so in preliminary results, we're seeing, so blue means like decreased traffic in the middle of DC and increased traffic around the 495 ring road. What does that mean for air quality emissions, health, and exposure? And Hoda's a student with me leading that. Another project that's going on, I see Mohammed Reza here, is modeling exposure to oil and gas development in Texas. And one of the things about oil and gas development is that it's a lot of different processes. So you have the extraction, you have storage, you have pumps. And so he's separating the different processes and looking at which of the processes where you could make an intervention is contributing most to exposure. This is Karnes County, Texas. They have some of the most oil and gas activity in the entire US. Okay, so where do we go from here? This is like my chance to be on a soapbox. Source specific PM 2.5 is important, but I think that it's understudied. And there are a few reasons why I think it's understudied. It takes a lot of data if you want to look at multiple sources across space and time. I mean, big data isn't something that a lot of the people here are unfamiliar with. Also, we have uncertain emissions. We really need the PM 2.5 species measurements to drive that. I think recently they're talking about potential cuts to improve in CSN networks, so that's not going to help. But we do know most of the processes that lead to PM 2.5. We know where most of the emission sources are. There are several new and old tools, like satellites are kind of exciting in this field to support thinking about this in new ways. And my last sort of provocative question is, this last study that I presented took a lot of work, because running PMF at every single monitor is a lot of work, and running CMAC is a lot of work. So are there ways to sort of operationalize estimates like this that would expand the health studies that we could do? I work with a great team, including students, postdocs, Daniel, and I think many of you have contributed data that we've been able to use. So I thank you for that. And I will stop there and take questions for 10 minutes. Thanks for listening.